Hello, this is Tom Seeley. I'm coming to you on St. Patrick's Day 2020. I'm doing so from my honeybee laboratory here at Cornell University. I'm sorry that I cannot be with you due to the global pandemic, but I hope you will enjoy this talk. As you can see, the title is The Lives of Bees, and in particular, we're going to be looking at how honeybees live in the wild. And until recently, this was an untold story. I want to begin by sharing with you this nice quote from E.O. Wilson. Apis mellifera, called humanity's greatest friend among the insects. And why is this bee our greatest insect friend? Well, for one thing, it's our single most important pollinator species. There was a recent study done by a team of several dozen investigators worldwide that looked across all of the crops grown on Earth and figured out for each crop what percentage of the pollination was done by honeybees versus other insects. And they came up with an estimate that 47%, nearly half of all crop pollination worldwide, is done by Apis mellifera, our little hero bee. A second reason that this bee is our greatest friend is, of course, that it's the honey maker. The honeybees are the makers of honey. This is something we humans have valued for thousands of years. Here's a nice illustration from a cave painting where we see two images drawn. What both images reveal is the risks that people would take to get honey. They had to climb up these vines or roots, whatever it was, high up here to dig out the honey from the nest here. And here's an even more dramatic one where the people got a rope, a ladder with rungs on it, but the nest is up here with bees flying around. You can see one individual is starting to fall off, and this one's leaping off, presumably because they're being stung. And then here's an image that shows very clearly honey production coming out of the bottling tank. I'm sure that's an image that is familiar to many of you. And I love this picture, by the way, because it shows both of these features of why this Apis mellifera is so important to us. It's this bee's carrying back a load of nectar, this nice translucent region of the abdomen shown clearly there. But she's also, this bee's collected pollen as well. So she's been out doing pollination. And because these bees are so important to us, we put them in artificial homes. This is a drawing from 1628, a Cosmographia. It's a massive book. I think it's about maybe 2,000 pages from the 1600s. It was one of the earliest encyclopedias. And one of the drawings it had in it is of this nice skeps. I believe these were in England, and these are wicker skeps, as you can see. So bees not living in the wild, but in human hives. And the real development in hives was, of course, came with the invention of the movable frame hive in 1851 by Lorenzo Lorraine Langstroth. And what this drawing shows nicely, so there's a wooden box. And his invention as we all know, was the bee space, the black portion around here. All sides of the frame are separated by this bee space, basically the width of a bee, and that enables the person to open up the hive, take off the lid, take out the frames, and look in at the combs. And Langstroth stressed in his early description of this his hive gives perfect control over the bees. And that's really, the Langstroth hive really lets us go into their lives and to a large extent control them, though not absolutely. Image that's probably familiar to us all. And I love the way of describing these hives to somebody that's not a beekeeper. I explain that these movable frame hives enable us to pull the combs out of a hive like you would pull folders out of a filing cabinet. Now that analogy is probably going to become less useful going into the future as fewer and fewer people work with filing cabinets, but it's good for now. And so we put the bees in these hives. And then we group the hives in apiaries. And both of these things are, of course, for our convenience, for the beekeeper's convenience, not the bees, not necessarily good for the bees, but very good for us. And because we do so much in terms of housing the bees and arranging their homes and things, they're often, Apis mellifera is often referred to as the domesticated bee. I would argue, though, that honeybees, however, are still essentially wild animals because, yes, we house the bees in our hives and thereby we gain control over where they live. And we also make it possible to go into their homes and take out what we want, the honey and beeswax. But when you think about it, we actually gain rather little control over what the bees do. After the bees fly out of the hive, they go wherever they want. And even when they're inside the hive, they're doing mostly what they want, building comb, rearing brood, collecting food, whatever. So I'd say that to the vast, the major extent, they are still in control of their lives. And one indication that Apis mellifera is not a flat out domesticated species is the fact that they very easily go back to living in the wild. For example, when a managed colony casts a swarm and the bees move into a tree, those bees are just fine in the tree. They know how to live in a tree. They've not lost their wild ways. And one thing I want to stress too is that these wild honeybee colonies, they're still important, at least in many places of the world. Often they will outnumber the managed colonies. And what we see here is a wild colony's home in a tree with its nest entrance here. And then this is this section of the tree which I have cut down and split off carefully one side of the nest to expose the combs. And you can see that it's a tall, elongate shape. Combs are built just like we have in our hives. Probably can't quite see it, but there's even little bee space, little passageways on the edges of the combs. Honey's stored in the top. One thing that's not clear, because I didn't put in a size scale, is just what the size of this nest is. It was basically a slightly more than a 10-frame Langstroth hive body. So it was basically one deep hive body. And there are, where I live in the rural parts of the Northeast, there are 2.5 of these wild colonies per square mile. So they're not terribly, they're not super common, but they're not terribly rare either. And one thing about these wild honeybee colonies is they are important in many ways. For one thing, they provide lots of pollinators for free. At the Cornell orchards, for example, there is a bee tree and on the edge of the orchard, and I approached the orchard manager to see if I could collect the nest, cut down the tree and collect the nest and the bees from that tree. And he said, "No way! I want those wild honeybees there to pollinate my apple trees." So, indeed, so wild colonies go out and provide lots of pollinators for free. Another reason why these wild colonies are important is, and maybe it's even more important, is that they show us the natural history of Apis mellifera. And why is that important? Why is it important for us to know what their true natural history is? Well, I think Wendell Berry expressed this issue very, very well in a book he wrote called Home Economics, and he wrote the following, and he was referring to agricultural animals in general. We cannot know what we are doing until we know what nature would be doing if we were doing nothing. In other words, we have to use the natural lives of animals, domesticated or animals that we rely upon, or even crops. The only way we can know what we were doing when we're using those animals is to know what nature would be doing, how they would be living if we were doing nothing. And that's particularly important to honeybees, because for thousands of years we've had honeybees living in our hives, and we've not been paying attention to how they live in the wild. And that's why this talk and this information is, to my mind at least, important. To be more specific, by looking at the wild honeybee colonies, we're learning how nature is solving a major problem of honeybee health. This is the Varroa destructor mite. And because the bees living in the wild, they're not being treated, they're not getting an assistance from beekeepers, but as we'll see, they are surviving and surviving quite well. And so we can learn from them how that works in the natural world. And we can learn some lessons from the bees, I feel. I'm going to show you this little video. It's just for fun. It shows this Varroa mite and how skilled they are as a parasite of our bees. In this video, if I can make it work, there's a little mite here on this daisy, on the petal of this daisy flower. I've trained a worker bee, to come to this daisy and collect sugar syrup off the daisy. And what you're going to see is how skillfully that little mite climbs onto the worker bee. Let's see, is this working? Here we go. Here comes our little bee. She climbs on. Here's our little mite. Watch what she does. Zips right up the hind leg, flips herself up onto the abdomen of the bee, and then goes down into the petiole. We'll see it again slower. She starts moving. You notice how she flips herself. It's like she's an acrobat onto that bee and then slides down the side of the abdomen. That mite knows all about honeybees, and that's part of why they're so problematic for us. I think we all know that depending on where you are, it could be 20%, 30%, 40%. Some large percentage of managed colonies die each year, and mostly from viral diseases spread by Varroa. Many of you probably know the most deadly of these viral diseases is the deformed wing disease. And here's an bee that illustrates in very sad detail just what happens to these bees that are infected with high loads of this virus. Their wings are deformed, as you can see, but also their legs are paralyzed. You can see this bee has got a leg, she's dragging here and here, and she has a stumpy abdomen. So very, very sad for the bees. And what's been the main response to the mites and virus threat? It's been to treat colonies with pesticides that kill mites. And this is, I think, a rather ironical advertisement by Formic Pro. Fast, easy, and effective. Safe. Here's the word safe, organic, safe with honeybee, with honey supers, etc., etc. Not obviously, clearly not terribly safe for the beekeeper who's wearing the vinyl gloves here and putting out these formic acid strips. And I don't know how many people here have used this, but those strips are very potent, very powerful release of the formic acid gas. And believe it or not, when you do this, you close the hive up and the poor bees are stuck in their hive with those fumes all around them. I don't think that's terribly good for the bees. Here's another example of our response, our main response to treating with pesticides. Here it's stressed that this is the apivar, the fluvalinate strip, and this was also claimed to be safe, but again, the beekeeper is wearing the gloves. And we now know that it's actually not entirely benign to the bees either. So these chemical treatment has been our main response to date for Varroa. But no surprise, the mites have evolved resistance to the pesticides. Honey can be contaminated with the pesticides, including this apivar material, and even the bees themselves can suffer damage from the pesticides. So that's one response to dealing with the mites, but I don't think it's the long-term or even a really good response. The alternative is what I like to call Plan B, and that is look to the bees in the wild to see what's happening with them. These bees in the wild are not receiving pesticide treatments. So so one question is, have they been wiped out by the mites or the viruses? And if they've not been, then how come? And this answering the how come question, as we'll see, has two parts. We'll be looking at, have the wild colonies evolved genetic resistance to the mites through natural selection? And we'll also be looking at, do these wild colonies have a healthy lifestyle? So there are aspects of not who they are, but how they live that are helping them deal with the mites. Well, let me, I want to talk in terms of direct experience. So I'm going to share with you a little bit of the history of the Varroa deformed wing virus problem in New York State. Varroa entered the United States via Florida in the mid-1980s, and Varroa reached Ithaca, New York sometime in the early 1990s. We're not sure exactly when. These were probably got from Florida up to New York carried by the migratory beekeepers who were bringing their colonies up from Florida where they overwinter, and they bring them up north for pollinating crops, particularly in New York State, pollinating apples. And whatever the mechanism and however the timing, all my colonies at my laboratory were laden with Varroa mites in the summer of 1994. And I knew they were laden by then because I would see in front of my colonies in August lots of dead and dying bees crawling across the grass in front of the hives. And I didn't know how to deal with the mites at that time. And all of my colonies, nearly all of my colonies, 17 out of 19 died over the winter of 94, 95. And I was dismayed by that. That was a horrible loss. But one thing I want to stress here is there were actually two colonies that survived, and they were doing well. And I should have learned more from those two colonies than I did. But I think I was just so upset by the heavy losses of the other 17 that I didn't focus on the fact that two of them did not die and were fine. Anyhow, I began treating my colonies for mites in the summer of 1995, and I was using the Apilife VAR and the Formic Pro and some other things, and the colonies were living, were surviving with those treatments, but if I didn't treat a colony, then they would die. So by 2002, I presumed that the wild colonies living out in the forests around Ithaca, I presumed they were all gone, all dead. But that summer in 2002, I decided to see if this was in fact true. Had the wild colonies really been wiped out? And I had a unique opportunity at this point, because back in 1978, I had surveyed the population of wild bee colonies living in a forest near Ithaca, New York. It's the Arnott Forest. Got Ithaca, New York here at the base of this long lake called Cuga Lake, and about 15 miles to the southwest is the Arnott Forest. It's a research forest owned by Cornell University, 6.5 square miles of forest surrounded by more forest, so you can see. And the reason this is so heavily forested in this part of south of Ithaca, and here you can see just how forested it is. You're up on the top of the hill, you look out, forest, woods as far as the eye can see, is because the land is very poor. We're up in the Appalachian Highlands here. It's poor land. It had been cleared in the early 1800s, but farmers quickly learned that it was not good farmland, and by the 1880s, the farms had been abandoned. So for the last 140 years, it's been growing back to forest. Anyhow, so that's the setting for much of what I'll be talking about, the Arnott Forest. And back in 1978, just as a matter of curiosity, I wanted to find out what the abundance of wild colonies was in a forest setting. So I went to Cornell's Arnott Forest and looked for the wild colonies. And in 1978, I had searched half of the Arnott Forest. This is our outline of the forest, irregular outline. And where it's green, it's forest. Where it's white, it's old fields, which have now, since 1978, they've also filled up with young forests. And In 1978, searching across half the forest, I found 10 bee tree colonies. One was just outside the colony, so I actually have to say there were 9 colonies in the forest, within the forest perimeter then. Now, I'll explain a little bit how I find them. And I want to stress now that I didn't search through the whole forest, but I searched through about half the forest, found 9 or 10, however you want to count it, colonies. And this illustrates what one of these wild colonies looks like. It's a large tree. This is a large old hemlock tree. There's a knothole in it, and bees are living inside a cavity there. And you can see they've put propolis on the bark around the nest entrance. Okay. So I had baseline data from 1978, and so I realized that in 2002, I said, okay, here is one place in all of North America where we have baseline data on the abundance of wild colonies. So in 2002, I said, I'm going to go back, I'm going to go to the same place, the Arnott Forest, same season, use the same methods, and the hunting will be done by the same person, me. And I fully expected, when I started this work in August 2002, I fully expected to find no colonies living in this forest, for I presumed they'd all been killed off by the deadly duo of Varroa mites and the deformed wing virus, which had, now at this point, in 2002, had been in Ithaca for the previous 10 years. You might be wondering, how does one find wild colonies living deep in a forest? The technique is by bee hunting. And how does one go bee hunting? Well, you start by going to an area of open where you've got flowers in the lawn. Here's a lawn area. This is the headquarters of the Arnott Forest, and I'm starting a bee hunt right in the lawn here. And what I do is I use a little contraption called a bee box. I capture bees off flowers in that bee box, and I capture the bees in the rear chamber of the box, and then in the front chamber I put in a little square of comb, which I've filled with sugar syrup. I let the bees enjoy that comb, and then I let them out of the box. They fly home, and then if the conditions are right, if it's not a honey flow on, the bees will recruit to that feeding comb, that little feeding station that I've created, and be a lot of bees, and there's a lot of bees flying back and forth. You can see the direction that they're going to fly home. And then step by step, you move the comb and the bees step by step towards their nest. And bit by bit, you work your way closer and closer to the nest, and you find their home. Now, here's an example of how one of these bee hunts works. This was not in the Arnott Forest. This was on the Cornell campus. And in this particular hunt, I started at noon, catching some bees on flowers in a garden behind the old president's house. And then I could see quickly the bees were going basically up to the north direction. So I came over here after an hour of letting the number of bees build up. I moved my feeding station here. It became very clear that they were going due north. So then I made steps about every 45 minutes, from first to here, then to here, then to here, then to here. Finally, around 4 o'clock, I was up at this station, and I was timing the bees. And the bees were telling me that we were very close to their home, because it took the bees only about 2 minutes to 2.5 minutes to leave the feeding station, go home, and then come back to my feeder. And I knew that because I had labeled bees with dots of paint, so I could identify individuals. That told me what I needed to do was just start searching in the direction the bees were flying, looking for their home. And what I found was the bees living in this oak tree up here in a knothole that was right there. And that was quite high off the ground. So you might be wondering, how on earth do you spot bees flying in and out of a knothole that high off the ground? The answer is, it's quite easy, because when you're looking up in the tops of trees, you see bees flying around, and our visual systems are very good at detecting motion. And under right conditions, you've got a lot of bees zooming in and out of a nest, and it's an eye-catching thing to see the eye-catching sight, to have that traffic of bees at the entrance of a nest. So to recap, 1978 found 10 colonies in or just outside of the Arnott Forest. And what did I find in 2002? Well, to my surprise, I found 8 colonies. And so really virtually the same density of colonies in the forest. And I'll just go through this slide a little bit to illustrate how I actually conducted the hunt in 2002. I started in the back entrance of the forest here, found bees on goldenrod flowers, and gave them the comb, started looking at where they were flying home as their numbers had built up, once their numbers had built up, and I could found that some of them were flying to the south, and I saw that some were flying to the north. So I first focused on the bees flying south. I worked my way down to the south um, by about a half a kilometer and found a bee tree there. And then, oops, then I came back here and then I ignored any bees flying to the south, focused on ones flying north. I worked up and found their bee tree. This is a little awkward. And then shut down, once I found those 2 bee trees, I shut down the feeding station here. I moved down the road, collected new bees off a new patch of flowers and looked at where they were going. Some were flying back to the first bee tree that I went to, back to A. Others were going up to a new bee tree. So step by step then, by starting different groups of bees, first here, and then capturing bees here, and then here, and then here, and then here, and then here, I worked my way around the western half of the forest and found 8 colonies living in the wild. So that basically, it was really clear. There were still honeybees living in the forest. 10 colonies, 8 colonies. I was surprised, but there it was. So that made it clear that there were colonies still living in the forest, but it didn't make completely clear how they were surviving there. And one possibility I had to seriously consider was the possibility that these wild colonies living up in this forest, which is in a remote part of the county, did not have Varroa mites. There are no beekeepers, no managed colonies within miles of this forest. So that, well, maybe these wild colonies up here are just isolated. They don't have Varroa mites. So what I had to do then was I put up bait hives in the Arnott Forest to capture one, so I could get some colonies living in a hive so I could check them for mites. And what I did is I take old 10-frame hive bodies, put in 10 old combs, mount them up in a little simple platform up in the tree, install them and put up 5 in May 2003, and 3 were occupied in July. Now I could look inside the colonies, inside the hives, look in the colonies to see if they have Varroa mites. And what I used a sticky board at this time, just a sticky board that was slid in underneath the screen on the bottom board. And these were the mite counts. Mites caught in 48 hours for 2 of these colonies. So in August 2003, there were a lot of mites. In September, still a lot. So relatively high mite counts in the fall, but the colonies survived winter just fine and came out in the spring with very low mite counts. And then they built up again. And then the colonies survived again. And here's colony 2. I don't have room to put in the information about colony 3, but it's the same pattern of moderate to high numbers in the fall, then lower numbers that build up in the summer, but the colonies keep surviving. And so, just to explain again, 1978, 10 colonies, 2002, 8 colonies, and then 2011, I did it again, so that every 10 years or so, I've been looking up in the Arnott Forest, and I found 9 colonies, searching always over about half the forest. So I do conclude now that wild colonies in the Arnott Forest are present, and they're somehow surviving with the mites and the viruses. So this raises the question, what's going on in the wild? How are they managing to survive? Here we come back to the questions we mentioned earlier. Do they have good genes, or good lifestyle, or both? Well, let's first look at the genetics of these bees. Do they have good genes? In other words, have their genes been tuned up by natural selection to give them mechanisms of resistance to the Varroa? The answer is yes. These bees do have genes for resistance to Varroa. And one of the pieces of evidence of this is that in the 1990s, I now know that these bees have experienced strong natural selection for resistance to Varroa. And the evidence for this is that there are very large genetic differences between the wild colonies of honeybees in this forest and in the other woodlands around Ithaca. Large genetic differences between the colonies before and after the arrival of Varroa in the mid-1990s. Now, how do I know that? Well, I know this because back in the 70s, when I was studying the wild colonies, starting to study the wild colonies, I collected voucher specimens. Every time I found a bee tree, I would collect about 40 worker bees, just swept them up with an insect net, and then I put them as pin specimens and stored them in the Cornell University insect collection. So in 2011, I went back and went again to found wild bee tree colonies in the Arnott Forest and other forests around Ithaca. And so now it was possible to do a compare bees pre-Varroa, 1977, and post-Varroa. And one of the indications that the bees underwent strong natural selection is there was a massive reduction in the number of mitochondrial or queen bee lineages between 1977 and 2011. You can see that in this diagram, which is basically a kind of family trees of queen bees in the colonies that I collected both in 1977 and in 2011. And you can see that back in 1977, these matrilineal or queen lineages had a lot of diversity. They had lots of different ancestries, those colonies. But now they have ancestry of just three roots. One of the wild colonies I collected in 2011 had an ancestry on this line. And all the others came from either this grouping here or this grouping here. So there's been a very large loss of the genetic diversity of matrilines. And the reason I keep saying matrilines is because I'm looking at mitochondrial DNA. And mitochondrial DNA is just passed from mother to daughter. So from one queen to the next queen to her daughter queens, etc. So we're looking at queen lines here. And the reason there has been this massive loss of diversity of the matrilines, queen lines, is because it's a marker of high mortality between 1977 and 2011. And that evidently that strong selection has produced a survivor stock. It's helped contribute to the existence of the survivor stock in the woods. And one thing I want to stress here was a key ingredient to being able to get this look back into the past was those voucher specimens in the Cornell's insect collection. If you're an entomologist, take note, voucher specimens prove valuable in ways you would never imagine at the time. So how then? So that we have very strong evidence from these genetic changes that natural selection has changed the bee's physiology and behavior. But how? Well, I don't have time to go through the details now, but I'll tell you a couple of things that these bees, in terms of their physiology and behavior, what makes them good at killing adult mites. Well, they're good at killing adult mites, and the workers are also good at disrupting the mites' reproduction. And one of the measures of their ability to disrupt the mites' reproduction is if we look at this, how well these wild colonies are doing when they're given the freeze-killed brood assay test. This is a test where you find a frame with sealed brood, capped brood, you put a cylinder over it. It's about 4 inches in diameter. You pour in a half cup or so of liquid nitrogen. You freeze and thus kill the brood. And then you leave that frame, put the frame back in, and you come back 48 hours later. Now, historically, the percent of bees, of the freeze-killed cells that would be opened up and the dead bee would be removed in 48 hours, was somewhere in the range of 30 to 40%. That's historical, pre-Varroa, unselected bees. Now, if you look at selected bees, and these are 3 lines, Minnesota Hygienic, Breeder, Vermont. These are 3 selected lines where they selected specifically for the bees' ability to remove freeze-killed brood. And they've got, in natural selection, artificial selection's got it up to 100% of the cells removed, cleaned out in 48 hours. And here's the Arnott forest bees. They are doing as well as these artificially selected bees. They're 98%, virtually the same as these artificially selected bees. And so one of the things that Arnott forest bees have going for them is this ability to clean out diseased brood. But unlike these bees, these Minnesota Hygienic and so forth, where they've been selected for just one trait, the ability to respond to freeze-killed brood, the Arnott forest bees have been selected through natural selection to respond to lots of things that will enable them to kill the Varroa. One is they're very, as I mentioned before, the wild colonies are very good at killing the adult mites. They will bite off the legs. If we collect Varroa mites under a screen in colonies, Arnott forest colonies living in hives, we will find that well over half the mites have either their legs removed or their carapace has been crushed. So they're very good at killing the adult mites and, as we've seen, disrupting their reproduction. So are these wild colonies surviving thanks in part to having good genes? Evidently, yes. We've seen 2 lines of evidence, both their behavioral changes and their genetic changes. But what about lifestyle? Yes, these wild colonies enjoy at least 20 advantages relative to managed colonies in terms of their lifestyle for helping them cope with Varroa. Let's go through some of these. One of the lifestyle differences that favor the wild colonies is the spacing of their colonies. The wild colonies are spaced about 0.5 miles apart on average, whereas in an apiary, and this is one of my apiaries, they're about, sometimes they're only half a foot apart. And you can all understand that when any organism lives more widely spaced, it's much less vulnerable to parasites and pathogens. And we're seeing that right now with the current epidemic, where in fact people are encouraged to space themselves out. Another aspect of the lifestyle of bees living in the forest versus in an apiary is that the size of the nest cavity or living space of the colony. Wild colonies occupy nest cavities that are much smaller than beekeepers' hives. And that's illustrated by this graph here, where it shows the size distribution of the nest cavities of wild colonies whose nests I collected and dissected back in the 1970s. And what you see is I'd get the bee tree, I'd find the bee tree, I'd cut it down, take out the bees, split open the tree, take out the bees, and then I'd refill the cavity with sand. And so I could measure with quite good precision the volume of each nest cavity. And you can see they tended to be in the range of 20 liters out to about 60 liters. And one deep 10-frame hive body, Langstroth hive body, is 40 liters. I don't know what a national hive size volume is, but whatever that is, it's probably not that different from a deep Langstroth. And so in the wild, bees are living in hive nest cavities about the size of one deep hive body. It would be an exceptional nest cavity to be as large as 2 deep hive bodies, and very exceptional to be in 3 deep hive bodies. And what does that mean? Well, living in a small nest means that the wild colonies are poor hosts for Varroa. They have less brood in their nests. And they have breaks. more breaks in brood rearing from swarming and from nests becoming honey bound. Um, in late summer, I know when colonies live in these nests, even in August, their their brood nests are shrinking because they're filling up their nests with filling up their combs with honey. So this is just this difference in the nest cavity size has huge impacts on the vulnerability to the Varroa. Another thing that the wild colonies have going for them in terms of lifestyle is that they coat the walls of their nest cavities with antimicrobial tree resins. And here's a bee, here's a resin collector bee. She's come home with the blobs of the resin. She'll go, we now know that these bees, when they come in the nest, they go up to wherever resin is being used and they stand around and wait for another bee, not a resin collector, but a resin worker, to pluck the resin, chew the resin off of her legs and apply it to the surfaces. And here's an example of, this is the floor of a wild colony nest where you can see even the floor surface has been glued, thoroughly glued down in place. So there's no cracks and crevices where bacteria could thrive in. And most of the propolis is used to seal off in the wild the fibrous walls of the nest cavity where the fungi have decayed the wood. So, and because these materials are antimicrobial, they also work against the microbes that are creating the deformed wing virus. But even more broadly than that, there's a general reduction in the activity levels of the immunity genes of bees living in and this is an experimental situation. If you put propolis on the walls of a hive and you look at the level of the immunity genes of the bees living in those hives and you compare them to the levels of the immunity genes in bees living in hives without the propolis on the walls, you find that they're much lower if they are living surrounded by the propolis. And what does that mean? Well, it's particularly important because of the young nurse bees are much healthier and their nutritional status is better. And I think we all know that the young nurse bees are the heart of the colony's health and ability to grow and stay strong and get stronger. There's a fourth difference in lifestyle between bees living in a forest versus in an apiary. In the wild, the colonies occupy well-insulated nest cavities. They're thick-walled, they're in a tree. And as we all know, our managed colonies, unless you're a very careful beekeeper and you're building your own well-insulated hives, managed colonies generally do not enjoy life in a well-insulated home. And to look at the impact of the difference between a thin-walled wooden hive versus a thick-walled tree cavity nest cavity. Working with a friend, Robin Radcliffe, we went to he owns a farm and he's got these nice old sugar maple trees along the road there. And working together, we cut out a square cavity the size of a natural nest cavity. Oops. And then we built a door so we could close the thing back up. And the door has an opening in it, like a natural nest cavity. And then for reference, I built another box, same dimensions as the cavity, whose cavity has the same dimensions as the cavity in the tree, but it's built out of standard lumber, as you can see. And then we recorded the temperatures, both inside the cavity. There are no bees in either box or tree cavity. We just recorded the temperatures at 2 points in each cavity, and we also recorded the ambient or outside temperatures. And you can see here's our ambient. That's indicated by the black line, the outside temperature. These are every 2 days, 2-day intervals here. So the ambient temperature, as you can imagine, it warms up during the day, it goes cooler at night, up, down, jumps all over the place. Well, the box basically tracks the ambient temperature. There's no insulative value, no cushioning of the swings of temperature. But in the tree, things are much more stable, much more stable. If bees were living in that tree, they would have a steady quite a steady um, temperature situation, very much. So pretty sure that we need to look more at this, but it seems quite clear that there's going to be less thermal stress on colonies living in tree cavities, and thus healthier. The bees are healthier thereby. So to summarize, what are the take-home messages from this talk? Well, I think there's several. Let's go through them. First, most fundamental take-home message, the honeybee Apis mellifera remains a wild animal. It moves easily from our hives to a hollow tree. Second key take-home message is wild colonies are still viable. They're good and they're still out there. They're still living, they're surviving. I haven't gone through the details of that. Some of them that I follow, the bee trees are continuously occupied for up to 8 years. Wild colonies are still viable. They're good sources of survivor stock. And by survivor stock, I mean bees that are adapted to surviving on their own in their location, even with Varroa destructor. And I think the third take-home message is that the way that these bees live in the wild is a good guide to us for how to improve our methods of beekeeping. So they better harmonize with the bee's natural history. And I've mentioned just a few of the ways of doing that to improve the hive insulation, make the hives smaller so the colonies have smaller brood nests, more prone to swarm, make the hives more widely spaced, roughen the walls, the inner wall surfaces of the hives, encourage swarming, and so forth. Now, these are a lot of things that run contrary to standard beekeeping practices, of course. But if we want to take advantage of what the wild colonies are showing us, then we would be adjusting our beekeeping, and so this is just a different approach to beekeeping. It's an approach that puts more stress on allowing the bees to live naturally and use all of the tools that they have to maintain their health, but involves reduction in the honey crops produced by colonies. It's a trade-off: greater health, less honey production. I hope you find that of interest. I thank you for your attention. What I've covered is the materials I've talked about today are based on the better part of 40 years' work. And so I'm just giving you a thumbnail sketch of what we know about this topic. And if you want to learn more about how honeybees live in nature and how to use this information, I recommend this book that I worked a couple of years on writing, The Lives of Bees. Same title as this talk. It tells in greater detail this story of how honeybees live in the wild. And if you're interested in it, but it tells not just what we know, but also in the last chapter, it provides some advice on how we can use this information to tune up our beekeeping. I call it Darwinian beekeeping. It could be called bee-friendly beekeeping, apicentric beekeeping, whatever. So that's my story for this talk, and I hope you find it interesting and useful. Thank you very much.